All right, so welcome. This is Common House Richmond. We're going to start down here in the basement. What you see here, it's all covered up. We've got a few photos of this stuff while it was in process, but this is a steel plate shear wall. We'll walk around the corner and you can see what one of those looks like not covered up. But this was kind of our central core, and you'll see when we go up to the lobby how we were able to integrate that into the existing diaphragm. So this is an existing building that is being fit out to house a new urban country club. So it was built around the turn of the century. It has cast iron columns, steel and timber beams, and then a timber floor system. We'll walk around the corner right here real quick. See here in the basement where these are the existing beams, and we sistered these up with LVLs because the existing floor system was not sufficient for a new assembly type loading. You notice the LVLs don't come all the way to the end. Wood can fail in either shear or moment. These were failing in moment, not in shear, so it helped a lot that we didn't have to bring these all the way to the end and land them on the existing steel beam. And this is a piece that's actually left over from the steel plate shear wall that we'll walk around the corner, get a quick look at. My name is Tom, by the way, and Michael is with me, who is an alumni of Virginia Tech, and I'm going to he's going to hand the phone to me in a second. I'll let him tell you a little bit about this steel plate shear wall.
Yeah, so I'm Michael. I graduated from civil engineering at Virginia Tech at 2018. I've been working at Engineering Solutions ever since. And so I'm going to talk about a little bit of these plate shear walls. So we're down in the basement now, so we're one level below grade. And you can kind of see the base of these things. So the columns that shoot all the way up the building are made out of rectangular HSS, and this was meant so we can fit it within a 2x4 wall up above. And what we used, instead of like your traditional X braces or chevron braces, we used just pieces of plate that we then could bolt, and it could all just be done in the field and give us the biggest amount of adjustability to get stuff in and out of here, because this was an existing building. And also, one of the really cool things that you can kind of see illustrated here is that we had a lot of new MEP equipment going in, a lot of new duct work, pipe work, stuff like that. So we really needed a lot of adjustability to be able to fit things through these walls. So you can see here that we were able to shift these things up and down, a few inches to allow these ducts to pass right through. So that really kind of streamlined the process and allowed like the entire design team to kind of function together pretty well. So right now we're in the basement, and we'll go up a couple levels. We can kind of show you where these things come up. They're finished up above, but we can show you some pictures of what they looked like before. But these things go all the way up the building on either side.
You want to talk about the footing real quick for him?
Sure. Yeah. So the footings of these things, so we're on the lowest part now, and we're actually standing on part of the footing. The loads on these are higher than we could achieve through just normal spread footings. So these are actually pile caps where we have helical piers that were drilled into the ground. They're basically like really big screws, and you just screw them into the ground until you achieve a certain torque, and that torque then is representative of a certain tension and compression load that we needed on either side of these. So we're actually standing on the pile cap here. This is actually a little bit of finished concrete that's on top of it.
Yeah.
All the way back in here, this is all standing on top of a finished slab that is on top of a pile cap, and then we have those helicals that are drilled. We have 4 on either side shooting out that way, and then 4 on that side shooting out that way.
Right, and that was done for both bearing and for uplift, because with any of these, I mean, it's a tension and compression couple with anything, and we don't have a big dead load coming down on these, so we needed those primarily for uplift. All right, so right now we're standing right above where that central core came up. It's right behind us here. You tried to put it down for this wall, you couldn't because it's all steel. The problem that we have is right behind you. We have a wall full of glass, right? So the building worked pretty well laterally up until it got to that point. At that point is where we had to transfer that shear back into this central core. We did that through what we initially designed as cables, but ended up as a steel plate, just for constructability. And so that runs from each one of these corners through the floor system to the top of the post here that has a steel, that then the steel plate shear wall goes all the way down to the basement and has that footing that Michael was describing to you. We tensioned those cables using an all thread that went through a couple of plates, and then we put tension on them just to give some initial tension to both of this. So as the building starts to ramp, these things can tighten out. So it was a real, and to get it through these beams here and the wood floor system was a bit of a nightmare. You'll see that in some of the photos that we will also include in this video here. So, as we walk around the back of the building, you can see some of the surgery we did there too. This big opening in the back side of the wall obviously was not initially there. We had to poke in a new steel lintel to that and combine a couple of openings that were already there. That becomes a little bit tricky for an existing building because there's lots of existing variables.
So here we're at the existing fire escape stairs. We had to add a flight to this, and you'll see in a second as we go up this big flight why we had to add all those new shear elements. Because we did basically a vertical addition on the roof. What was an existing roof now became occupied space. So that triggered us by code to have to make this building work for modern lateral load. So this is still place that we put the tube right here, and then we went up one more level with this fire escape. And now we see rooftop bars. This is what it's all about. So real quick, we'll talk about kind of the way this got constructed. This was the existing roof right here that had a pretty good pitch to it. We reinforced this by adding steel below it, and then a steel deck, and then all of this structure here is kind of like your standard residential deck. It's sitting up on posts and pressure treated wood to give it a level basically playing surface. So beneath it, water flows through that and then down through this, off, into this gutter. So this stuff is here. Yeah, you can see where the fire escape is. Well, we also added a pool. So it's not common that you add a pool to a building built at the turn of the century that is cast iron columns. So the basic structure type that we came up with here was steel beams that span from wall to wall that carry all of the dead load of this structure. Right? And on top of that is a metal deck, and then a plywood deck, and then this sort of overbuilt on top of that. While it sounds like a lot, it's a pretty light floor system, and it's a pretty long span for the steel beam. So that kind of is a recipe for vibrations, right? So once I get, several people up here walking around, you might feel some uncomfortable vibrations. So what we did to sort of arrest that was to add, after all of this was installed, and the pool was even filled, so they temporarily filled the pool, we added neoprene springs on top of the steel beams, between the steel beams and the column below. And so what that did was allowed us to manage the load onto those cast iron columns, because cast iron fails suddenly and catastrophically. So we only wanted to add a load to that we felt comfortable with. So knowing what the deflection of our steel beam was, and the thickness of that spring, we can manage that load and take the bounce out of this floor system. So, and walking around up here, it feels pretty solid. So, I mean, again, you know, it's hard to see in here, but some of those, the steel plate shear wall that Michael was showing you downstairs is more or less kind of in this area-ish, right?
Mm-hmm.
Yeah, and it grabs this floor system and then grabs each floor system as it goes down and brings it all the way down to that foundation that then transfers that into the earth, and then we're good. So, any questions? No, obviously.
So now we're down on the 4th floor, which is the level just below the deck. So what you can see is you can see some of the existing attic. So you can see the existing attic joist, and beyond that was the original existing roof. So what you can kind of see right up there is the bottom flange of one of those new beams that we put in. And coming down right here, we have a cast iron column, and you can see the little stub post that then is welded to the bottom flange and sits right on top of the top of that existing cast iron column. So you can see that that's where we used those neoprene spring pads that Tom was talking about. On this side, we can see where the beam terminates into the existing brick masonry wall. So what we have on these exterior walls is original existing 3 wides of clay brick masonry. So this is actually the most heavily loaded beam we have right above us.
Yeah,
right
that's
here,
right. The
because
pool's
this
on
is
top of it, right? Yeah,
directly
yeah.
below the pool.
Yeah.
So not only did we have the highest load, but having the lowest amount of perceivable deflection was very important. So we had to figure out a way to take that load, and once we got it to the end walls, how do we transfer it into these clay masonry walls? So we had originally come up with an idea of just bearing them directly on it and spreading that load down onto rebuilt clay masonry that would distribute the load down. But for constructability purposes, they didn't want to have to build scaffolding on the outside. They wanted a solution that they could do from inside the building. So we came up with these very large anchor plates that we have basically a plate that goes from here all the way up to where the beam frames into it as a simple shear connection. And we have 3/4 inch, or actually these ones are 1 inch anchors that are epoxy drilled in epoxy into the masonry wall. So at the bottom here, we took out 1 life of brick, so that sits flush right inside the wall. And the bearing of this plate is 4 inches. So it sits right up tucked into 1 life of masonry. And we added some stiffener plates to just give it some more increased stiffness. And then we ran lines of bolts, and each beam down this entire line has a similar connection to this. The number of bolts varies based off of what load is on it. But this one you can see was the most heavily loaded one. So I think this one ended up having 18 bolts on each side.
And we stuck it into the wall to eliminate a little bit of eccentricity, because if we stick it on the face of the wall, we have a lot more eccentricity or bending on that wall, and old masonry walls don't like that so much.
Exactly.
So, yeah.
And then up above this, it's just a simple shear connection that frames right into this this anchor plate.
Yeah. You can see a little bit through so the brown things, that's the existing attic framing. That all of this steel was put in, basically threaded through it from above. There was an existing roof that they tore off, and then they put the steel on top of this, left the attic framing in place, walked on it in places, and so that's the floor system that I was just describing up above there.
What you can also see is, so this is the big girder here that we were talking about. So then we have intermediate steel beams that are spaced at about 8 foot on center, and so they run this way. It frames into another steel beam that's directly above us here. And this is where the pool is actually sitting. So we have these intermediate beams that run this way that are spaced out. And we have timber 6x6s that just run continuous across those that become the surface that the pool is supported by.
Right. And as far as we know, that's the first known use of CLT in Richmond.
Yeah.
Yeah.
There we go.
If we can call it CLT, really it's screw laminated timber.
NLT.
More NLT, yeah. But we've got some photos of that in progress as well. And that again was done just to keep weight down. This is your shear wall right here, right, Michael?
Right.
Yeah.
So this wall's finished right here. So this is directly above where we were showing you the foundation to that exposed shear wall below. So they come all the way up to here, and they fit within a 4-inch stud wall right here. And then they go up and connect to our diaphragm up above, our new diaphragm for the pool deck level. But those shoot all the way down the building, and that elevation is very similar to what you saw in the basement, where they have different size plates, mostly half-inch, or they're all half-inch thick, so, ranging from 18 inches wide to down to 12 inches wide, and just spaced throughout so that we could fish things through the wall as needed to put all this new mechanical equipment in. One other challenge that we had was some of these floors, the loading wasn't changed to a point where we were increasing the load, but some floors were, where we were creating assembly space, like this floor above us, where we're adding a restaurant. So it originally was multifamily, so we were using 40 PSF live load, whereas now it's assembly space, so we want to use 100 PSF. So we showed you in the basement what some of the sistering of each one of those joists look like with an LVL, and that's done above us too. But where those frame in, the existing buildings have these wood girders, where it's five plies of like true 2x12s that are all nailed together, and they stand between the cast iron columns, as you can see that bearing line goes straight down. So one of the challenges we had was these things weren't enough to support the increased load, so we had to store them up too. Yeah. And we didn't want to replace them. So what we did was, you can't see it here because it's all covered up, but we took C8 channels and put a channel on either side of the beam, and then bolted it through the whole thing, and then created a new connection where we welded it onto the, or we actually drilled and tapped a bolt into the cast iron column, so that we could take the new load and put it onto the channel, and the channel supports all the new live load, whereas the dead load is already in place and sits on the wood that's there. So that's how we took care of strengthening up this floor.
Right. Now we're outside, and you can see sort of the issue that we were dealing with. All glass on the front end, but then above that, a lot of glass, but a lot of masonry as well. And so we were able to show that worked laterally, and that's what we had to do from the bottom up. But hopefully sometime soon, maybe later in the fall, we'll actually be able to come here and get a drink. So we'll see. All right, let me flip the camera and Michael will say hello, and then.
Yeah, so this was a really fun project to work on. We got to work with, a bunch of different design challenges, a bunch of different materials, everything from steel, cast iron, masonry, concrete, wood. Covered all our bases there. So this was one of those projects that's just like, you really have to get here, you really have to dig in, you really have to tear off the walls and see what's actually back there. A lot of testing and that went into it. So it's cool to see that it's taking shape, and hopefully it'll be open for business very soon. So.
All right, very good. Have a good semester.